So, chapter, we're going to go over the operator method, which is a very, very powerful method to solve higher order non-homogeneous differential equations. Order 8, order 17, whatever order you can imagine, kind of in a blink of an eye. You'll see. All right. Well, first of all, let's talk about operators and their properties. How we have really seen them before, but we didn't work with them or we didn't use them that often. All right. For instance, so far we have looked at differential equations with the prime notation, that is the Lagrangian notation, symbol for the derivatives and its corresponding orders, or the Leibniz notation when we see the ratio of the change of the dependent variable with respect to independent variable. We need to introduce a new operator. Actually, I talk about this at the end of the homogeneous equations of higher order. But today we're gonna dive into this in a deeper manner. All right. Well, so in calculus one, you may or may not have gone through another notation for the derivative. So just like y prime, this is differentiating. So an uppercase D on the function we want to differentiate with a subscript x. This is to indicate that we are differentiating with respect x, or simply d brackets y, all right? Actually, the subscript x would help if we happen to have a function of multiple variables that resembles a lot to the partial derivative, all right? So just like we see something prime or dx of something, well, that's an operator, just like ddx of x squared, for instance. What is that equal to? Isn't that 2x? Well, so that quantity or that symbol, rather, ddx by itself, this is an operator. This is the differential operator of order 1 because it's asking us to find the first derivative. And it's actually telling us an instruction, which is to take the derivative with respect x. All right? So just like, for instance, what about these two? So d of this quadratic polynomial, this d is asking us to differentiate this polynomial, which is x8x minus 6. All right? That's just a derivative. And in a similar way, differentiate the exponential function, which is 5e to the 5x. All right? I mean, there's really nothing special yet. Uh, we can also describe higher order differential operators. For instance, the second derivative, which is the derivative of what we already took the derivative of, which translate or rather reduces into d squared. So that tells us take the second derivative of the function y. All right, that's all it tells us. And we can generalize this idea by y up superscript n, which tells us to take the nth derivative of the whatever function. Like third order derivative, 17 order derivative, 95th derivative, whatever. All right. Well, with this, we're going to create a framework to represent these sums and differences of derivatives in terms of operators in order to get an alternative solution to these differential equations, especially when the orders of the differential equations are pretty high. All right. So, okay. Well, you'll see as we get through the example. So number one, let's fun and play with this operator. So write the following derivative expressions in terms of operators or vice versa. Write the operator version into derivative form. Well, what do we have here? Y double prime, which is d squared, all right, minus 5 times d, okay, plus 9 times y, all right? And well, actually, let me put the y in brackets just to follow the notation. And guys, that actually looks very similar to something we did before. Remember the characteristic polynomial? It looks exactly the same, except that we have it in terms of d, of uppercase d. So should make a pretty cool connection with something we did before. What about this one? So third order derivative, that is d cubed plus d squared, okay? And this operator is acting on the function y, all right? Now let's do it the reverse way. We have it in terms of operators. Let's write it back in terms of y's and y primes. All right. So 3dy first of all. So the constant remains the same. The d when it acts on y that turns into a y prime, and the reason to that is because it's simply d raised to the invisible first power. So we just find the first derivative. And lastly, this -7 multiplies with y to, yeah, to multiply with y. All right, there's nothing special about it. All right, what's next? So 4d squared, that turns the y into second derivative plus 9y, right? So all we're doing is just going back and forth between operator and Lagrangian notation for primes. All right. Now, here is the thing. This operator notation also works when we have differential equations with variable coefficients, not only with equations it's not limited to equations with constant coefficients. How do we do this? Well, we simply replace the prime notation. So we're going to have this acting on some y equals to 0. But what do we have? This is the second derivative d squared, and just keep the variable coefficient. Just like we kept the constant coefficients, keep the variable coefficients. All right? Plus 2xd plus x squared plus 1. And all of this is going to act on the dependent variable y by taking its corresponding derivatives and multiplied with whatever coefficients, whether these are constant coefficients or variable coefficients. Okay. All right, guys. Well, now that we had a glimpse of what operators are, let's have a look at some of its properties. And well, properties, I mean, operators in general are not commutative, as we will get to see with some examples here. All right. So here's the thing. Uh, let's consider the following operators here. So number one, how about we compute this? Well, notice in this case we have a sequence of operators that we're going to do on the variable y. And guys, how do we perform this operation? Order matters because we have the dependent variable here, which is where the operators are acting on. So we do the first operator, or rather the closest to the we do the closest to it, right? In this case, this will be keep the 3d, and then this d, what does that do? Find the first derivative, keep the 2, and that becomes a y prime. All right. What's next? What about 3 times 2? Isn't that equal to 6? And take the derivative of what we already took the derivative of. Isn't that now the second derivative? Okay. Wait. That'll be 6y double prime. All right. Once we do the operations the other way around. All right. So have this operator act on y, keep the 2d, and dy becomes y prime. However, keep multiplying with the 3. What is 2 times 3? This will be 6, and then dy prime. Isn't that the second derivative? All right? So these two are the same. Also, this is the same as saying 6d squared acting on y. It would have been exactly the same. All right? Okay. Letters C and D, we're gonna see something very interesting. So this time we have a product of operators, where one of the operators is accompanied by a variable coefficient, not a constant coefficient. You will see what's gonna happen here. And again, we perform the operator that is closest to the dependent variable y here. In this case, take the derivative. So keep the xd. What happens when we do dy? Doesn't that become y prime? Okay, it becomes a y prime. All right. What else do we do? What does the d do on the y prime? Doesn't that do it a y double prime? Keeping the x in the very front, that's x y double prime, right? So that's what we're going to get here. All right. Now let's be careful with the next one, okay? Because here we're going to have a little issue. So, okay, so number one, what do we do? So, D acts on, what is that? On Y, right? And that's to give us D times X, okay, times Y prime, all right? However, check this out. Okay, actually, let me do the following. Let me do instead D acting on X, Y prime, okay? Which means, okay, now what happens if the operator D acts on this expression? Do you guys agree that inside of the bracket we have a product of two functions of x? All right, that y prime, yes, it's the first derivative of some function of x, so this is a function of x. So we need the product rule. So to differentiate this product, the derivative of x, which is 1 times y prime, plus the derivative of y prime, which is y double prime times x. And well, simplifying this, this is y prime plus x, y double prime. All right. And well, as you can see, these operators or these results are not the same. What does that mean? Our conclusion tells us that operators with constant coefficients are commutative. However, operators with variable coefficients are not necessarily commutative. All right. Well, maybe in some situation, one with variable coefficients may end up being commutative, but that's not in general true. All right. Okay, so let's compute one more. Okay, so let's compute one operator. Well, let's say we have this operator of the form d um, plus 3 times d minus 1 times y. All right, so I'm going to show you this operation in two different ways. So I'm going to have the first operator act on the function y, keeping d plus 3, and this will be the derivative of y, which is y prime, and negative 1 times y, that's minus y. All right, and furthermore, I'm going to have this operator d. Okay, check this out. The d operates on the two functions here, giving us the derivative of what we already differentiated becomes the second derivative. The derivative of y, that's y prime, and then 3 times y prime. Actually, no more brackets here. And then minus 3y. And well, how about combine like terms? Plus 2y prime minus 3y. All right. So that's the result of doing this operator. The other way around, okay, the other way is to actually perform the product of the operators too, because, and we can do this because these are technically variables, technically operators with constant coefficient, and there are constant terms. Okay, so this would be d squared plus, or rather minus d plus 3d minus 3, which, and that acts on the function y, which is d squared plus 2d minus 3 on y. Do you guys agree we're going to get the exact same thing? All right. This will be y double prime plus 2y prime minus 3y. Same result. All right. Okay, guys. So now that we have an idea of how operators work, let's talk about a very special operator. One operator we call the exponential operator. And this is going to be, this tiny operator will be the magic touch to solve this humongous, huge differential equations. You'll see. All right. Well, the exponential operator tells us that e to the negative ax times d times e to the ax equals to d plus a. All right. How about that? Well, let me actually prove that result. Okay. So, number one, I'm going to have this given operator. So let's say we have some y function being multiplied by the exponential function of the form ax. And you might wonder, why am I introducing this a to the e8, e to the ax function? Because wasn't the form of this solution of this equation of exponential form? So we're going to get somewhere. And then I'm going to have the differential operator acting here. All right. So on the one hand, okay, let me have these operators act one at a time. So I'm going to distribute the exponential with the y, keep the operator d, and then this is e to the ax y, and then let's expand this operator. But again, guess what? We're going to have to use the product rule of differentiation, right? So that means, okay, the derivative of the exponential, which is a e to the ax, y, plus the derivative of y, which is y prime, times e to the ax. What am I going to do here? Factor e to the ax. And that's going to leave us with y prime plus ay. All right? Guys, doesn't that look essentially like the characteristic polynomial or auxiliary polynomial? I mean, we're just getting this from a kind of a funky way, right? And even better, check this out, guys. We can write this guy in terms of operators, okay, e to the ax, and I'm going to write this d plus a acting on y, all right? Okay, acting on y. Well, where are we heading with all of this? Okay, I'm gonna set this guy equal to that guy. All right. So d e to the ax acting on y equal to that result. E to the, and I'm gonna please leave some space after the equal sign. Acting on y. Okay. Now, I'm going to simplify this expression here by multiplying both sides by e to the negative ax. However, I'm not going to multiply it by e to the negative ax, just multiplying. In linear algebra, there's something called multiplication to the right or multiplication to the left when it comes to matrices. You may have seen that before. So, because the order of the multiplication of the matrices actually matters. So, in this case, it also matters with operators. I'm going to multiply e to the negative ax to the left, all right? To the left. Okay, so we may go ahead and simplify some factors here. Okay, cancel these two. All right. Actually, we can divide out the y's, and that's going to leave us with e to the negative ax d e to the ax equals d plus a. And that's what we wanted to prove. All right. We wanted to show. Well, of course, you guys are not responsible for memorizing or knowing these proofs. I just want to derive the results to make connections with linear algebra, with how operators work as well. The point here is to know how to use this operator in practice by solving the differential equations. Okay, so the operator d plus a equals e to the negative ax, d e to the ax can be used to obtain the particular solution, the y sub p, for higher order non-homogeneous linear differential equations with constant coefficients. So you'll see how this is going to be very, very helpful. In some cases, we may want to avoid, what is that? Undetermined coefficients or variation of parameters, which depending on the complexity of the y sub p, a problem like that could be a nightmare. All right. I mean, and yeah, we solved a few of those that end up being nightmares, right? All right, well, let's solve this differential equation y double prime minus y equals e to the x. Although this equation doesn't seem that hard to solve using, what is that, undetermined coefficients, let me show you how we use the operator method to solve this. All right? Okay, so I'm going to write the left-hand side of the differential equation in terms of operators, all right? This is d squared minus 1 acting on y, okay, equals e to the x, okay? I'm going to factor the difference of squares in terms of operators, that is d minus 1, d plus 1, acting on y, equals e to the x, all right? Okay, guys, so I'm going to use the exponential operator to transform this polynomial into a product of exponentials and operators, and you'll see what's going to happen here. Okay, so the first operator, okay, let me highlight it with one color. So we use yellow for the first one. So the operator d minus 1. Okay, do you guys agree that this is, okay, this d minus 1 is the same as saying, well, it's, yeah. Okay, no, maybe over here. D minus 1 is the same as saying d plus negative 1. All right? Sometimes this is a little tricky when it comes to writing these operators. So I'm going to replace this in terms of operators. So whatever number goes here, it goes in the you see after the plus sign, it's going to go in the second a. So this will be then uh, e to the negative 1x, all right, d e to the negative x, okay? And then for the second operator, d plus 1, well, this is already a 1, so that's going to go e to the also negative x. Okay, let me change color. E to the negative x, d e to the x. Because in this case, a equals to 1. In this case, a equals to negative 1. So we just changed the sign. And that equals to e to the x. All right. All right. So let me rewrite all some of this. So e to the positive x, d. Let me combine these two together. This is e to the negative 2x, d e to the x equals e to the x. Okay. And let's solve this for oh wait, I forgot to keep writing the y. We need to because we want to solve this equation for y, right? That's the solution. Okay. So actually I would like to well, the way we're going to go about this is to eliminate everything from left to right until we get with the y by itself. First of all, we're going to divide by e to the x, divide by e to the x. Okay, this is going to leave us with d e to the negative 2x times d e to the x, y equals to 1. All right, the next step is to check this out, to divide by d. All right, okay, but guys, what does it, okay, so we are eliminating the derivative operator, okay, the differential operator by doing essentially the inverse of it. But guys, what's the inverse of the derivative? The integral, right? Okay, so check. Eliminate the d's. Turn this 1 over d into, first of all, e to the negative 2x d e to the x on y equals So I'm going to use the same color green. So the derivative in the denominator, which is inverse, would be the integral with respect x of the function 1. What's the integral of 1? Isn't that x? Okay. So this is e to the negative 2x d e to the x acting on y equals to x. All right. Let me continue up here. Okay. So what should I do here? Okay. I'm going to actually divide both sides by e to the negative 2x. All right. That's going to leave us with d e to the x y equals x e to the 2x. Okay, let's keep going. What do we do? Divide both sides by d. All right, while we cancel the d's here, the 1 over d here becomes, well, let me write that what I'm left with, e to the x y equals the integral of x e to the 2x with respect to x. Any ideas how to evaluate the integral on the right-hand side of this equation? Integration by parts, right? I'm going to skip the process. You guys at this point are experts in integration by parts, right? So e to the x acting on y, so that equals 1 half x e to the 2x minus 1/4 e to the 2x. So that'll be the result of the integration by parts. Okay, what do we do next? Finally, to get the y by itself, divide by e to the x. And this is y, finally. This is y, but this is y sub p, okay? Equals to 1 half x e to the x minus 1/4 e to the x as well, okay? That's only the y particular. Guys, the y homogeneous, you can simply use the polynomial in D, turn it into a polynomial in m minus 1, m plus 1, equals, what is that? Equals to 0, and m equals to 1, m equals to negative 1. So y would be the y homogeneous, I mean y sub c plus y sub p. How do we get y sub c? We got m1 and m2, which are repeated solution, no, not repeat, non this real and distinct, c1 e to the x plus c2 e to the negative x plus, what did we get for our y sub p? All this. Um, Plus 1 half x e to the 2x, no, e to the x plus 1/4 e to the x. Final answer. All right. Yeah, check this out, guys. Let's compare with what we did back with, what is that? Undetermined coefficients. Do you see the homogeneous solution? How it actually has a repeated, it has a duplicate with the non-homogeneous part of the differential equation. We would have had to multiply by 1 power of x, do a couple of derivatives, and then equate coefficients. Well, instead, we have a more stepwise road to get directly to that y sub p. All right. I mean, if you want to try the same problem using undetermined coefficients, you should get exactly the same. All right. Let's have a look at another example. Okay, so letter B, y prime, yes. Oh, shoot. All right, yeah. So before we finish this one, okay, this is y equals to, because this guy is right here. Okay, let me change highlighter. Um, C1 e to the x actually absorbs with these two, right? Because they are essentially duplicates, right? Thank you, thank you, thank you. So this is C1 e to the x plus C2 e to the negative x plus 1 half x e to the x. Final answer. That was our official final answer. Thank you. Thank you. Okay. Let's have a look at the second example, letter B. Y double prime plus 4y prime plus 4y equals to x to the negative 2 e to the negative 2x. Okay, guys, unfortunately, we can't solve this differential equation using undetermined coefficients because the algebraic part multiplying the exponential has negative exponents, and that's actually restricted from the list of functions for which undetermined coefficient works. So that means we should use variation of parameters. We have to find the Wronskian, finding integrals, having these crazy products, maybe a little tedious to do. Well, as an alternative, we're going to use the operator method. Well, let's write the left-hand side of the differential equation. That is d squared plus 4d plus 4. All of this acting on the function y, okay, equals to x to the negative 2 e to the negative 2x. All right? Okay. So what's next? Let's factor the polynomial. Actually, this is d plus 2. Whoops. D plus 2. D plus 2. Do not write it as an operator itself squared. Keep it in factor form, okay? You'll see why. That's because we need to write one operator for one exponential operator for each of these two. That is x equals to the negative x, x to the negative 2, e to the negative 2x, right? Okay, so for the first operator, again, the operator e to the negative ax d e to the ax. This is our operator. Again, let's use it. And for a equals to 2, we're going to have e to the negative 2x d e to the 2x times actually the same, e to the negative 2x d e to the 2x. All right? All of this acting on the function y equals to x to the negative 2 e to the negative 2x. Okay, so let's simplify whatever we can. Now, check this out. This will be canceled out, right? Because same base, opposite sign exponent, boom, they go away. All right? That's going to leave us with e to the negative 2x d times that's actually d squared, right? Is that d squared? Okay. Uh, e to the 2x, all right? Acting on y equals to x to the negative 2 e to the negative 2x, okay? All right, well, let's keep dividing, okay? Divide both sides by e to the negative 2x, e to the negative 2x, okay? This will be equal to d squared e to the 2x acting on y equals to x to the negative 2. All right? What's next? Division on both sides by d squared. Okay? So we need to compute the inverse of the second derivative. All right? The inverse of what's the inverse of the second derivative? Wouldn't that be the double integral? Okay, so let's divide out these two first. Okay, and this will be equal to, this will leave us with e to the 2x acting on y equals the double integral with respect x twice with respect x of the function x to the negative 2. Okay, let's evaluate the first integral of x to the negative 2. Isn't that, okay, first of all, e to the 2x acting on y equals the integral of negative x to the negative 1 dx. There's one more iteration of the integration left, all right? And let's compute this integral right here. What is that equal to? So this is still e to the 2x acting on y, but it's a negative natural log of x, right? okay? And dividing both sides by e to the 2x, this would give us with this would leave us with y sub p finally negative e to the 2x ln of x. Isn't that, guys, better than doing variation of parameters, finding the Wronskian? Potentially, well, it would be time-consuming Wronskian because of the repeated. We would need to use the protocol when computing the Wronskian and then setting up two humongous integrals. Well, this is way quicker. All right. For y sub c, now turn the equation in terms of d, turn it into an equation in terms of m. So m plus 2 times m minus 2. What do we, oh, actually plus 2 on both. So this is m equals to negative 2 repeated. All right. Okay. So what's next? Y equals to y sub c, the complementary solution, which is the one related to the homogeneous equation, plus the particular solution, which is the one we just found in the previous few steps. So because we have a repeated solution, this is c1 e to the negative 2x plus c2 x e to the negative 2x minus e to the 2x ln of x. Try this using variation of parameters and you should get the same. Negative 2x isolated x. Which one? This one? Oh, yes, yes. This one. Thank you. Yeah. Thank you. Thank you. All right. All right. Let's do one more example and call it for the section. All right. So, what about this eighth order differential equation? Guys, just think about it. Okay? Do you want to do undetermined coefficients taking egg derivatives? With yes, and this is going to be a repeated solution. You'll see how. All right, that's number one. Number two, do you feel like doing variation of parameters with determinants of matrix of egg by egg, a total of 9 of them? Do you feel like doing that? I mean, okay, can you envision the amount of work? I mean, guys, even if you use the internet to solve the problem step by step, to just inputting the entries of 9 egg by egg matrices, thanks but no thanks, right? All right. Well, let's write this in terms of operators. Okay, so this would be d to the egg plus 8, d to the 7th plus 28, d to the 6th plus 56, d to the 5th plus 70, d to the 4th plus another 56, d to the 4th plus 28, d, wait, 56 d to the 3rd, right? Plus 28 d to the 2nd plus 8d plus just 1, right? All of this madness here acting on the function y equals e to the x. All right? Okay, guys. How do we factor this 8th-degree polynomial? Any ideas? Do you want to do rational root theorem with this? No, check what's on the next page. You guys remember Pascal's triangle? You can easily generate the numbers by simply adding 1 plus 1 equals 2, 1 plus 2 equals 3, 2 plus 1 equals to 3, 7 plus 21, 28. Well, what about these guys? Okay, check the coefficients of the equation here. Do you see the pattern 1, 8, 28, 56? Okay, so do you see it? 1, 8, 28, 56, blah, blah, blah. Okay, these are the coefficients of a plus or minus b to the 8th power. All right. However, this is even better. This even better. I don't know what happened here. Yeah. This even better reduces to the following. D plus 1 to the 8th power acting on y equals e to the x. All right. If you expand that binomial to the 8th power, you should get that polynomial. All right. Okay, well, but actually, we need to expand this 8 times. I mean, write it as a product of itself 8 times. You'll see why. D plus 1 times D plus 1 times D plus 1 times D plus 1 times D plus 1. Tell me when to end. D plus 1. That's 4, 5, 6, 7, 8. One more, right? D plus 1. All of these guys acting on y, all right, equals e to the x. All right? See, this problem is more bark than bite. You'll see. Okay, guys. Well, we need to write one operator for every single factor you see right here. That is e to the negative x d e to the x, that's 1. E to the negative x d e to the x, that's 2. E to the negative x times d e to the x, that's 3. E to the negative x d e to the x, that's 4. E to the negative x d e to the x, that's 5. E to the negative x d e to the x, that's 6. E to the negative x d e to the x, that's 7. E to the negative x d e to the x equals, is that 8? Equals e to the x. Okay, guys, just check this out. You're gonna love this actually. Cancel, cancel, cancel. Goodbye, 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 goodbye. Thank you so much. How many D's are we left with here? This is gonna leave us with e to the negative x. Is that d to the 8th power? All right. Times e to the x, okay, acting on y equals e to the x. All right. Well, let's do the division on both sides by e to the negative x, e to the negative x. Uh-huh. All right, that's d to the 8th, e to the x, acting on y, equals e to the 2x. All right? You guys agree with this? Okay, well, let's divide both sides by d to the 8th, d to the 8th. Well, the inverse of differentiating 8 times, what is that? So, guys, remember those triple integrals from Cal 3? No, no, no. Again, those are already kindergarten integrals compared to this. You're going to solve this problem like a real rock star, like a boss. So, check. We're going to evaluate the 1, 2, 3, 4, 5, 6, 7, 8. 1, 5, 6, 7, and 8. All right? E to the 2x. All right? We're going to solve this problem using an octuple. No, no, not triple, not double, no, octuple. This is a whole nother level, guys. And well, yes, that problem seems huge, but check this out. What happens when you integrate this guy, the integral of e to the ax, all right, dx? This is 1 over a, e to the 2x, all right? What if you do this a second time? The double integral e to the ax dx, if you integrate this guy, you would get 1 over a squared, all right? E to the 2x. Now, in general, integrate dot dot dot, integrate n times e to the ax dx 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 n times. This is equal to 1 over a to the n e to the ax, all right? Well, so this octuple integral is going to be evaluated in one single shot. So this is e to the x acting on y equals 1 over 2 to the 8th e to the 2x. What's 2 to the 8? Is that 256? So this is 1 over 256 e to the 2x acting on y e to the x. And one more step here. Divide both sides by e to the x. And this is our y sub p finally 1 over 256 e to the 2x. But if you guys want to verify that using undetermined coefficients, be my guest. All right, but don't try it at home. Okay, well that's y sub p. All right, for y sub h or y sub c, what do we have? M plus 1 to the 8th power, okay, equals to 0. What is this? M equals to negative 1. Repeat it. 8 times. All right. Final answer. General solution y equals uh, y sub h plus y sub p. Okay, yeah, it fits. So y equals c1 e to the negative x plus c2 x e to the negative x plus c3 x squared e to the negative x plus c4 x cubed e to the negative x plus c5 x to the fourth e to the negative x plus c6 x to the fifth e to the negative x plus c7 x to the 6 e to the negative x plus c8 e to x to the 7 e to the negative x plus the particular solution, which is 1 over 256 e to the negative x. All right? Final answer. End of the section.